But also to be fair, several okay, let's get started. Sorry, few minutes late. Today is off for me, you guys. You can sense I'm on edge. And I apologize ahead of time for not being myself. Anyway, how was the exam? We'll find out. We'll find out. Did you overthink it?
Yeah. No, you told us not to.
Okay. I will post the key for you guys, but again, when you look at the key, maybe I shouldn't post the key until you get your exams back. Yeah. Right? Because if you see the key and you look at the answers, you go, oh no, I'm getting 0.
Right.
So no, I won't post the key then. I'll wait until we grade it. Okay. So usually I finish ASH analysis in one lecture, so that's why I don't have recap for you, but I can ask you questions. Why do we measure ASH content? Yes. Go ahead.
The total, so we can find total carbs.
Yes, so we can find total carb for the nutrition label. So we do ASH and moisture, although that we don't put them on the nutrition label, we measure them. Okay, that's one thing. Another thing, go ahead. First step for measuring mineral contents. Okay, that's very good. Give me an example of potential underestimation of ash content. Go ahead, Alicia. Flattering. So that's why those of you that had cheese, we dried it for you because moisture content is high, especially for cheddar cheese. And we also did the smoking on the hot plate so that you don't have this charring, splattering, all of that. Okay, that's very good. Another common example for underestimation. To high blood temperature, what will happen? So too high of a temperature is a correct answer, but what happens when you really evaporation of organic? Evaporation of the organic, you want them out, right? You don't want the organic to evaporate some of volatiles like iron, copper, zinc. Yeah. Okay, so what about overestimation? A very easy one for overestimating ash content. Very easy one, the opposite of what you just said. You didn't burn off all organic. So you wasn't hot enough, or you didn't leave it long enough, or the matrix is complex. You needed to put a little bit of nitric acid in there to help it. So yes, another one that is common when you're preparing your samples. You are trying to mill the sample in a metallic grinder, you might get contaminated. All right, so good. So we talked about dry ashing. What does dry ashing entail? What do you do? You all did the lab, so what did you do for dry ashing? What did you do for dry ashing? You weighed the samples, and where did you go with it? We put it in the muffle furnace. We put it usually at around an average of 500 degrees C. Depending on the method, the official method of analysis, depending on the sample you have, sometimes we put 450, 475, 525, it depends. And then we leave it there most of the time overnight. But each sample of food, each kind of food require different time and combination. Sometimes you take out the sample, put nitric acid, because some organic matter is harder than others to incinerate. And then after that, you take it out, you put it in desiccator, you come and weigh it. Very, very simple. So you have the weight of your crucible and you get the weight of your ash, and then you determine ash content. Okay, so I'm gonna move into wet ashing. Wet ashing is not used, and underline not used. It's gonna be helping you to answer some of your lab report questions and then some of test questions. It is not used for determining ash content. So wet ashing is done for specific mineral analysis, especially for those minerals that can be volatile in using a muffle furnace and ashing at high temperature. So this method combines the heat and acid to digest the sample and get rid of all organics and keep the minerals in solution. So basically with ashing, you take it, there is a digestion unit that you can get, and you can have multiple digestions happening in the same time. So you put in your sample, specific weight of your sample, and you add a combination of acids, either nitric perchloric or sulfuric nitric, combination of two strong acids. And then you use some heat, but the heat is not as high as 500 degrees Celsius, it's about 200-ish degrees. And then what happens with the combination of corrosive acid and temperature, all organic matter will be digested and converted to, or oxidized, converted into a CO2, SO2, NO2, evaporate. And then what's left in solution of the acid is your dissolved minerals. So you will see, because acid digestion causes like this burning, so the sample color changes from like burning dark black color to brown, yellow, and then clear to straw yellow solution. That's when you have all your minerals, and then you take it out, you dilute it, and then do exactly what you did for atomic absorption. Dilute it, and then prepare your standards and measure your minerals of interest. Mostly for labeling purposes, for determining iron content accurately, mostly we use wet ashing rather than dry ashing to avoid evaporation. So the advantages of wet ashing over dry ashing is you limit evaporation or loss of some volatiles. So here are some advantages and disadvantages. So minerals remain in solution. Remember when you were doing the atomic absorption lab, you had your ash and you needed to add concentrated acid and make sure your minerals were dissolved in the acid, and then you did dilution. Here, at the end of the digestion, your minerals are in solution. You don't have to worry about getting them in solution. You just do the specific dilution. And no volatilization, and then the oxidation time is short, few hours rather than having to put it overnight in the muffle furnace. So these are the good things. Of course, nothing comes without a price. So disadvantages include that you can't just leave it like you leave the muffle furnace, put in the samples, go, come back. So you need to be around. You're working with corrosive acids, so you need the proper training and safety measures. And you can only handle small number of samples depending on the digestion unit that you have. Now, another thing I forgot to mention is when we use perchloric acid, this is such a corrosive acid, you have its own hood. So we only have potentially in the department one perchloric acid eligible hood, and it's in a very small tiny lab that we don't use for that purpose. So anyway, because most labs or most hoods are not equipped for that, most of the time we use the combination of sulfuric and nitric acids. Okay, so that's that. We can reduce the time of ashing by using microwave ashing. And we can have dry microwave ashing, and we can have wet microwave ashing. The only thing with microwave ashing, as far as I know so far, I don't know if they've done anything different, and it's not an official method of analysis. Although they've done comparative, like running multiple samples and comparing regular muffle to microwave, and they find good comparability, but they didn't do enough uh, validation. For a method to be an official method of analysis, it has to be validated in many, many labs. So, but it is very efficient. You can do it in minutes. The analysis can be done in minutes. And in microwave, you can increase the pressure so you can have higher boiling point for the acid. If you're using wet ashing, you don't want the acid to evaporate. Yes, Greg.
You say that way back.
Microwave. Microwave ashing, whether it's dry or wet. To my knowledge, we don't have an official, doesn't have an official method designation unless I'm not aware of it. Okay, but if you are doing wet ashing, you might get units like this unit where you actually operate at high pressure. Then the acid will stay in solution and you won't lose it due to evaporation, and it becomes more efficient. Therefore, you can use less corrosive acids. Nitric will be efficient. You don't need perchloric acid. You might not need combinations of acid, because what you did to combat that is you can have higher temperature under higher pressure and have more efficient digestion. And multiple samples can be processed, but it depends on the unit that you obtain and the number of tubes you can put in there. So that closed system here, you can increase the pressure. This one here is open and it's used for larger samples, and you can see only 2 samples can be done at a time, and you cannot pressurize it. It's open vessel. This is a microwave dry ashing unit. We don't have it, but it's efficient. It's more expensive than the regular one. Yeah. So that's that. I have a last question for you for ashing, and then we can move to fat analysis. Let's take out a piece of paper for +2 for everybody and write down your answer, complete answer to get credit. And then we can discuss. Take a couple of minutes and then we can discuss. All right, who's willing to answer the first component? Yes, Haley.
I disagree, but actually, this is actually, just for the person.
But just to be specific,
It's for specific minimum.
yes, you want to start with when you talk to your boss. That's correct, Haley. But when you're talking to your boss, you want to start saying, you're correct about less time consuming. But I do believe that with wet ashing, based on this reference, is not used for ash content, total ash content. That's why we cannot use it for getting the ash content. Okay. So not considering time issues, why might you want to continue using dry ashing and why might you want to change to wet ashing, Emmeline? Exactly. Your actual time, hands-on time, is less with dry ashing than wet ashing. The total analysis time, yes, it is longer to do dry ashing. Another issue you would want to consider with your boss. What is it other than your attention, Mitch? Yeah.
Oh, she said, but actually, uses three, so it's probably more sensitive.
What uses it more safety issues. So you have to have safety measures taken using corrosive agent. And also you need some cases particular hoods. Okay. And if you are not really wanting to do those analysis of those volatile minerals, then you can do dry ash. If it is really, you want to determine the content of volatile minerals, then yes, you would do wet ash. All right, this table here is FYI so that you can determine, sometimes in a quiz, hypothetical situations, I might ask you come up with your own data and determine ash content. What does it mean come up with your own data? Weight of the crucible, weight of the ash, weight of the sample. So you want to come up with reasonable data and come up with percent ash that is not much greater than 2% or 3%. If you make up your own data and you get an ash content of 20%, that's not reasonable. Most foods have less than 10% moisture, even even less than 5%. Okay, so that concludes the ash. We can move on to fat analysis. Yes? We have a question in the chat. Okay. If ashing is being done, I think Rob was answering the question for credit. So it's not a question. So we'll give Rob the credit. Okay, but you guys in the room, you just have a complete answer and give Saj or not Saj, sorry, Sharu or Andressa. Okay. Let's see. Why is it not moving? I really don't like this. All right, let's see what you know. The following is true. A. It's just A. So the lipid, usually when we say lipid, we are not just distinguishing whether it's fat or oil. And fat has a higher melting point because it exists in solid state at room temperature under regular atmospheric pressure. And it's the other way around. Oil has less saturated fat typically than fat. Okay. What about this one? Okay. Well, B and C is an answer. Any other answer? Go ahead, Rachel. Huh? Just B. What were you going to say, Alicia? It's all of them. So vitamins that are fat-soluble vitamins are A, D, E, and K, right? They are, when you're extracting fat, they stay with the fat component and they are part of the lipid portion because the definition of lipid is anything in your organic, in your food that is not soluble in pure water. Need organic solvent. That's the simplistic definition of lipid. So vitamin A, D, E, and K will be part of the lipid component. And then what's considered a polar lipid? You know, usually fat is not, you think of it as non-polar. Yes, phospholipids are polar, like relatively polar lipids. So not all lipid components can be completely extracted using any solvent, let alone ethyl. Because of the very wide range of constituents within the lipid fraction, sometimes we need multiple solvents to extract the fat. So just the definition, I already told you the definition. Any component within your food matrix that is not soluble completely in water, pure water, or requires organic solvent to solubilize. So that's what the lipid is component. Just little, very, very brief refresher from what you learned in food chemistry. So we have different classes of lipids. We have the simple lipids, which you already know, triglycerides, for example, which are esters of fatty acids, and then di and monoacylglycerols. So these are simple lipids as well. And esters, fatty acid esters, but with a different alcohol, like retinol palmitate is vitamin A. Compound lipids, phospholipid is a compound lipid, meaning you have here in the picture, you have one phosphate, two fatty acid, and a glycerol. So that is your phospholipid, and this is what makes it relatively polar. We have lipoproteins, we have glycoproteins, cerebrocytes are usually found in cells, biological functions. They have like a fatty acid chain, they have carbohydrate, galactose, and they have an amine group. So these are just different components, but mostly in food, we have the simple lipids and potentially derived lipids. So in some oils, we might have free fatty acids, even during, we'll talk about fat characterization later on. Some processes like deep frying the oil, like you have potatoes, and you're trying to deep fry it, so you have this water, you have heat, triglycerols into free fatty acids. Who's trying to break in? All right. So if we have broken down lipids, sometimes we have free alcohols in there, hydrocarbons from the fatty acids, and so on, and fat-soluble vitamins. So these are just different types of lipids. They have different solubility, and that's what's important for us for analysis is realizing the different components within lipid extraction will make determining fat a little bit. We need to pay attention to those differences when we select the type of analysis we want to follow. If we know about the food and the type of lipids in the food, will help us determine what solvents we want, what method to use, and so on. Okay, so why is it important to analyze fat content? Typical question for every component of food. Yes, Sumili?
Something or like difference.
So standard of identity, let's say that. Let's say we want to determine standard of identity. We need to determine the amount of fat for specific foods that have standard of identity to make sure they're not adulterated, they're not processed in a manner that is not acceptable. And what else? Very simple. Nutrition label. Yes. What else? Very important when we talk about food quality. What's important? What lipids? Go ahead. Okay, that's fine, Rachel. So what's that? Stability, yes. What were you gonna say? Health concerns. When we do fatty acid, when we do fat characterization, we'll talk more about health concerns, but you're right, when we get a total fat, people that want to reduce total fat in their diet, it's important for them to know the total fat content. But when we have metabolites of fat, then we have other health problems, and we'll talk a little bit more about that later. Oxidation, that related to what Rachel said. So when we have high fat content, also depending on the type, polyunsaturated, saturated, that impacts the shelf life product. Okay, so that's, you covered it. Sometimes also we have manufacturing specifications. So it's not really only standard of identity, but let's say you want to produce skim milk. Or what's the fat content of skim milk? 0. What is the fat content of reduced fat? 1% or 2%. It would say on the label 2% milk, 1% milk, skim milk, full fat. So you would want to determine what is the fat content you want to get to based on the specification you lay out for your product. Okay, so that's all great. We can now move into the different, many analytical methods. Okay, so we have a range of analytical methods that we use solvents, organic solvents. So it's mostly we get the fat out of the sample and weigh the defatted sample or weigh the fat, or there are methods that you actually use. Well, before I get to that, we're going to talk about continuous methods, meaning you're continuously extracting fat using solvent in a closed continuous system, and I'll talk about that. Or semi-continuous, like the socks that we did in the back. That was semi-continuous. Do you remember what your PA told you and why it was semi-continuous? Yes? Yeah, so there is a soaking step. So the solvent evaporates, goes up to the condenser, comes down, and stays in a compartment, then it siphons back. Did you see the siphoning? That was my favorite part of Soxer. It siphoned back into the original flask. So that's semi-continuous, and then the discontinuous, you did Mojournier or Mojo or Mojiner, whatever you want to call it. where you put the solvents, shake, 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 extract, pour, and then do it again. That's discontinuous batch extraction. And then we'll talk later on two elevated pressure temperature systems, supercritical fluid extraction and accelerated solvent extraction. But don't worry, I have those abbreviation on different slide. And then the GC method, which you did already in the lab, and this is the official method of analysis for determining fat content for nutrition label. So you determine all of the fatty acid, not just what you did in the lab, you did semi-quantitative. But this one, we get all the standards of the fatty acid, we determine every fatty acid, and we convert to weight, and we add glycerol weight to it and get the total amount, calculate the total amount. Okay, so the other ones, non-solvent, mostly used for dairy products. So the Babcock and Gerber are used for milk, cream, and cheese. And here you don't use solvents, you use acid digestion, and you determine the volume of fat, not gravimetric, so volumetric. We'll talk about those. And then instrument-based method, the IR, we talked about it, near IR, mid-IR. Fosler method is based on measuring the density. And NMR is another method that is very simple if you just put the sample and get the results at the end. Anyway, it's instrument-based method, very accurate as well. Okay. So we'll start off with the sample extraction methods. So for sample preparation, we take into account the type of food, the nature of lipids, and extraction method available to us. So type of food, when I say type of food, what am I really thinking of? The matrix of food? From the food samples you worked in the lab, how are they different? Sierra. Moisture content, very good. We had to dry because when you're using solvents in a substrate, the moisture in the lipid will prevent the solvent from solubilizing the fat, will intervene in the solvent reaching the fat and solvent. Very good. So moisture content is important. What else is important?
Okay, it's high fat.
High fat or low fat. So when you have low fat product, what else is in that food sample? Either high in or high in. What did you do in the lab in Formosa? First step forward. What was your product? Parmesan. Okay, well, but that step was done for you. So we probably won't remember what it is because you didn't do it. You ate it, so yeah. Yeah. So if you have low fat, most likely you have a high carbohydrate protein product compared to the fat. So you have your fat really entangled in a high carbohydrate setting and a little bit of protein. So you add the acid to break down everything so you can remove that entanglement, and then you add your solvent to get the fat. That's especially important for high carbohydrate products. For cheeses, the step that you didn't do was done for you because it was time consuming. We add ammonium hydroxide to solubilize the protein. Otherwise, you have the cheese, you have the protein in a gel-like format, and the fat is entrapped. So you won't be able to extract the fat out if you don't break down that matrix, the protein matrix, or the curd structure. Okay, so we have to break that so that we can extract the fat. So the type of food is very essential in determining How do we approach it? Do we need to dry it? Do we need a digestion step? Soxit, for example, is really good for nuts and meat, high fat. You know, you don't have to digest much, so the fat is readily available, especially when you dry the meat, then it's mostly fat and a little bit of protein. So if you do Soxit, you have good, reliable data. Okay, so based on what we know about the method and the types of lipids, so do we have mostly triglycerides? If I know that I have mostly triglycerides, maybe petroleum ether will be enough, or hexane will be enough. If I have a little bit of polar lipids, non-polar lipids, then I need a mixture. I need a little bit of diethyl ether, a little bit of fat ether combined so that I can get the phospholipids out, the triglyceride out, the different polarity of the lipids taken into consideration. Okay. So we just kind of answered this. So who would like to give it a go? Okay. All of the above. Now, pre-drying may be needed. So I would say all of the above because it says may include, not should include. I would say pre-drying, the common thing we follow, if the moisture content is higher than 10%, then we pre-dry. If not, we don't need to pre-dry for Soxit, for example. If we're doing Mojo, we don't pre-dry. Why do you think? From doing the lab, what did you do for Mojo analysis? You had the sample. We didn't evaporate the water. Later, we evaporate the water. Any water that comes from the aqueous phase, contamination.
I think it's fine because we shake the same.
Yes, good. Yes, so we shake, we pour and do it like 3 times, 3 times. So in Soxit, do you shake? No. So if we don't shake, we don't force the solvent to reach the lipid component, dissolve it, and bring it down to the solvent. That's in Soxit. But in Mojo, we kind of force it to kind of interact with this lipid component. Especially, it will be easy if we did the acid hydrolysis or the NaOH solubilization with the shaking. We don't need to pre-dry. Okay, particle size reduction, always. You might, for best results, you want about 40 mesh. Do you remember the mesh number? What does it mean from your earlier chapters back in September? What's the mesh number? It's the number of holes per linear. That's the only, it's an inch, but linear instead of a square. Yeah, so the more the higher the number, the smaller the particle size is, and the higher the surface area, the better the efficiency of the extraction. Okay, so this is just example showing you like a flour sample already have really low fat content. So if you don't do acid hydrolysis, you're really going to underestimate your fat content. And if we try to calculate the percent relative error, that's going to be really high, close to 30% relative error. So that's just one example. So the hydrolysis really gets you more out, more fat release and better, closer to accuracy than without. All right, now selection of solvents. So in the ideal world, you need all of this. So you don't want to use any solvent that will have, what does it mean, solvent power? Meaning it solubilize also protein and carbohydrate. You don't want a solvent that could get the protein and carbohydrate as well. You want low boiling point of the solvent so that you can readily evaporate and you don't have to have high heat to evaporate. Non-flammable, you don't want accidents. Non-toxic, obviously. Non-hygroscopic, what does hygroscopic mean, or non-hygroscopic? Huh? Yes, Sumili? Yes, hygroscopic means if methanol is hygroscopic, so it has tendency to capture moisture, and that reduces its efficiency to solubilize fat. Inexpensive, isn't this a requirement for everything in life to be inexpensive? So. Is there one solvent with all these characteristics? We wish, but no. So in lab, you either use petroleum ether for Soxhlet, or you use the combination of ethyl ether and petroleum ether. That's the kind of the solution. I just answered the question, combine. But ethyl ether is generally a better solvent for fat because it's not really specific for polar or specific for non-polar lipids. Kind of gets different varieties of lipids. Whereas if you have a sample high in triglycerides, petroleum ether will help solubilize it better. It targets more the very hydrophobic lipids. Ethyl ether is more expensive than petroleum ether. However, also it's more flammable. Both are flammable, but one is more flammable than the other. Ethyl ether is hygroscopic, so that we capture moisture. The petroleum ether is not as much. They're very close in boiling point. Petroleum ether has a higher boiling point, maybe a little safer. We can increase the temperature a little bit. And then the solution we combine. So in Soxhlet, you didn't combine, you only use petroleum ether. Why? How many milliliters did you need to add in your flask? Do you remember? 300 milliliter. In Mojo, do you remember how many milliliter you use? 25 milliliter. Okay, so in Mojo, we can afford combining because you only use a little bit of volume, whereas in Soxhlet, you need that larger volume. Okay, goldfish is the method I worked on when I was a student and a TA, and I caused an explosion. Yes, let me tell you the story. Well, before I tell you the story, I'll tell you how it works. We don't have time for either. All right, we'll continue on Friday and I'll tell you the story on Friday. Maybe I'll be in better mood so I can tell it and enjoy it. Okay, see you on Friday.
Oh, yeah. And it was a goldfish.
Goldfish.
With the.
You know, it's CH, sorry. It's some good catch.
Is that the person's last name?
Yeah, absolutely. It's always the person's last name.
Like they name it. Something cool about those.
Another participation. Did you capture that? Yeah.
What's the kind of put into my lecture one day, or anything else?